All right, we're going to put together chapters 10 and 11. Okay. The first one's about gases by themselves, and then it's about how gases interact with each other. So they belong, they're both on gases, they belong together. Yeah. Which what? Oh, no. When we get done, your job is going to be to answer that question. Keep that tank in mind the whole time. We're going to start talking about things that would affect the tank today. It's still your job, okay? But I'm going to convince you and hopefully help you figure out what's going on with that tank, because you still have to figure out what's going on with that tank. I told you that you probably wouldn't get it right the first time, but you got some things in your head, and it didn't quite sound right when you were talking about it, did it? There was something missing. So we're going to get those missing pieces. Okay. So the explanation for why things happen with gases is the kinetic theory. Okay. Now, kinetic has that K-I-N-E root word. It's the same one that's in cinema. It's Greek for motion. So cinema was moving pictures, so they put the C-I-N-E for moving. Okay. So the first moving pictures were called a kinescope. Okay. Looking at moving. Okay. So the kinetic theory says molecules are in constant motion. Anybody think of a piece of evidence that makes you know that molecules are in constant motion? How do we know that? How do we know that molecules are in constant motion? What have you seen that could prove they were moving? Well, actually, it may not be something you saw. Maybe it's something you smelled. Because smells move. Smells move. Because I'm putting perfume on, not so that it's so that I smell good to me. I don't want the perfume to stay right on me. I want it to move a little bit, but not too far. That's actually something we'll look at later, is how do we decide how far it's going to move. Okay, to give you other evidence, things you haven't seen, I've got a little video to show you.
This is what many people think of when someone mentions the word molecule. A collection of brightly colored balls stuck together in a particular way, with each ball standing for one atom. Sometimes it's better to think of molecules like this, as millions of tiny, fast-moving particles. It might seem a little strange to think of something as tall and solid as this bridge as being nothing more than a collection of fast-moving particles. But this is the way the atomic molecular theory looks at matter. We know that molecules are so small that even the largest ones are barely visible through the most powerful microscopes in the world. So we can't see the molecules in the bridge, but we can see indirect evidence that nearly everything around us is made up of tiny, fast-moving particles. And this machine will provide the first piece of evidence. Here is a piston that can slide up and down. Under the piston are some BBs. If we turn on this motor and touch the piston to this vibrating bit, the BBs are sent jumping. See how the continual bombardment by these very small BBs holds the piston up. If we put a weight on top of the piston, it goes down a little. But the bouncing BBs still hold it up. It certainly seems that a continual bombardment by smaller objects can hold up a much larger object. Here is a similar cylinder and piston. But this piston has no BBs under it. We'll blow air in under the piston, then close the valve so that none of the air can escape. Now, what's holding the piston up? The piston is being held held up by air, but it acts just as the other piston acted when it was being bombarded by the VVs. Something we can't see is holding the piston up. It certainly seems that air is made up of tiny particles, far smaller than the VVs, and that these particles are bombarding the piston and holding it up. The name we use for these particles is molecules. Now, let's look at another piece of indirect evidence. The marbles here are a lot smaller and lighter than the sponge, but if there are enough of them, and if they're moving fast enough, they can push the sponge around. In other words, a lot of fast-moving small objects can push a large object around. Keep this in mind as we look at the next demonstration. With this device, we can capture smoke from a match in a chamber, and then examine the smoke with a microscope. The bright spots are smoke particles magnified 100 times. What's making them dance around? What's pushing them? This Brownian motion, as it is called, is caused by air molecules which push the larger smoke particles around, just as the marbles push the sponge. The movement of the smoke particles is more indirect evidence that air is made up of molecules. Air is a gas. What about a liquid? Water seems to come out of the tap in a continuous stream, but the atomic molecular theory says that almost all matter is made up of molecules. So we should be able to find evidence for molecules at work in the water. This chemical is made up of tiny chunks of material too small to be seen except with a microscope. If we mix some of this chemical with the water and put a drop of it on a slide, we can then use a microscope to see what's going on inside the drop of water. There it is again, Brownian motion. Something is pushing the chunks of chemical around. Water seems to be made up of molecules too, and they are pushing the chunks of chemical around, the same way the air molecules push the smoke particles around.
So, tell me, why did I bother to show you that movie? Oh, all four of them are true. All four of them are true. But only one of them is the right answer. Okay, so the answer is, of course, you have to let it be. Let it be. Okay, because this is responsible for all of those. Right? So we need to think about our understanding of why gases do what they do are going to be based on picturing molecules bouncing like those BBs. And that's the picture you need to have in your head. And what changes how they bounce. Okay? So first we got to talk about what's bouncing. So that kinetic theory of gases makes some assumptions about gases that are not true. They know they're not true, but they make the math easier. And they work pretty well. Later on, we'll see what we do if these assumptions aren't true, what we have to do. It's not that we can't do it, it's a pain. It's doable, it's just not fun, not easy. Actually, not even that hard. It's tedious. Okay? So a gas is composed of particles, and they said they were molecules. Sometimes they're just atoms. They're never formula units. I feel a little bad for you guys. A couple weeks ago, I gave you this mole worksheet where you figured out how many grams and how many liters and how many representative particles it was. You figured out how many liters of sodium oxide. Sodium oxide's ionic. you're not going to turn it into a gas at STP. You're not going to turn it into a gas at all. Yeah. Nobody thought about that piece of it. I'm okay with that, but I don't want to mislead you forever. Okay? Sodium oxide would not make a gas. Okay. Now, but we're going to treat them about a little bit specially. One is we're going to be consider that they are hard spheres far enough apart that we can ignore their volume. What the heck does that mean? Well, if you get pieces far enough apart, you can ignore how much space they take up. Picture this. You're in the bathtub. Somebody throws in a dozen bowling balls. Could you ignore the space that the bowling balls were taking up in the bathtub? No. Okay. Now, a hot tub. You're sitting in a hot tub with a friend. Somebody throws in 12 bowling balls. Are you going to notice those 12 bowling balls? Yeah, you're going to stub your toe.
Depends on the size.
Okay. Swimming pool. If you throw them in a swimming pool, are you going to notice those bowling balls very much in a swimming pool? Okay. And notice that the bowling ball is about this big, and about how many bowling balls could you fit into a swimming pool? Well, somewhere in the thousands, right? Well, that's really about how far apart molecules get. Remember, 18 milliliters of water is a mole of water if it's liquid. 22.4 liters if it's a gas. So over 1,000-fold increase. So it's more like the bowling balls in the pool than the bowling balls in the bathtub. If they're far enough apart, we can ignore how much space they take up. Does that make sense now? Okay. And what's between them is nothing. If you take the molecules out of air, what are you left with? Nothing. Completely empty space. Scientists fought this for a long time because they didn't think you could make something that was completely empty. But it's the only explanation. There's nothing there. So we got those particles. What are those particles? It's called the kinetic theory, so those particles must be moving. The particles are in constant random motion. Why is the motion random? Not attractive forces. Oh. They just bounce off each other. Can you control how they're going to bounce? It depends on what angle they run into each other, which way they're going to bounce, right? So it's completely random just because they're bouncing. And they're going to hit each other in different angles. That's what makes it completely random. I know your book broke this up into 5 pieces, but it doesn't take 5 pieces. We got molecules, they're in constant motion, and collisions are perfectly elastic. So when they collide with something, it's perfectly elastic, which leads us to one question. What the heck is elastic? Because this is not the elastic I know the definition for. If I asked you for the definition of elastic, that would be some stretchy stuff, right? It would be a noun. Here, elastic is not a noun. It's an adjective. It's modifying collisions, right? Okay. So elastic to a scientist means that it bounces off without losing any energy. That they don't stick together at all. Okay? So to a scientist, there's always 2 kinds of collisions. An elastic and inelastic. I lost my inelastic. Where'd my inelastic go? How'd my elastic? Okay. The whole world is in. I guess I have to get some. Oops, somebody took my other one. Okay. So when they hit each other, they don't stick at all. They bounce off each other. Now, are either of those 2 things true? Okay. Do molecules take up space? Yeah. Should we ignore their volume? Not really, but we're going to do it anyway. Hey, do molecules stick to each other? We had this whole section on intermolecular forces, and they were all attractive, right? They never repelled, they always attracted, right? So molecules are really sticky. Some are more sticky than others. We know that's true, but we're going to pretend they're not. We'll deal with the real world later. Okay. Said they're moving. How fast? Pick a number. Okay, it's 1,656 kilometers an hour for those of you who live in the English world. That's just over 1,000 miles an hour. That the average oxygen molecule in this room is moving at 1,000 miles an hour. Ow, one just hit me. We are getting pummeled all the time. Okay, and when you go up in the mountains, there's fewer air molecules, so they pummel you a little less. And your ears pop. Because pummeling is pressure. Okay, so they're moving at 1,000 miles an hour. Okay, how come when I turn on this gas jet, Harrison can't smell the gas? Because this is actually, I can tell you, later on we'll figure, these are moving faster than oxygen. So they're moving over 1,000 miles an hour. How come he can't smell it? How long would it take to get from the front of the room to the back of the room at 1,000 miles an hour? Yeah, almost, you wouldn't notice it, would you? But the smell's not there yet. Why not? Because, because the room's full. They don't get to travel very far before they hit something. The average distance they travel before they hit something is less than a centimeter. So they're moving at 1,000 miles an hour, but they only get to move at most about a centimeter at a time, and then they bounce off in a random direction. Every centimeter, they're changing direction. Are you going to be able to predict where they're going to end up? And are they going to get from the front of the room to the back of the room very fast? No, at every collision, they're going to move in a random direction. So there's a 50% chance they'll go further away, 50% chance they'll go closer back to that middle. But you know, they either move away or farther away or closer together. Or they move left or right. You do quadrants, but further away or closer together. Those are the two ways. And so that's how things spread out. Random bouncing. Random bouncing spreads them out. Okay. And that bouncing we feel as pressure. So if they're moving 1,000 miles an hour and we're getting hit all the time, how come we don't feel something hitting us at 1,000 miles an hour? The really, really tiny things. The BBs are way too big. A BB at 1,000 miles an hour will put a hole in you. I know when you get them up to about 100 miles an hour, they'll go right through your cheek. Well, no, they won't go through. They'll stop halfway and you have to cut them out from the inside. No. That's what friends are for. When he shoots you in the face with a BB gun.
I love that.
Okay. So now it's time to figure out what the heck temperature is. Okay. Kinetic energy and temperature. They're tied to each other. Kinetic energy is the energy something has just because it's moving. If you step in front of a bus that's moving, it has energy, it can give it to you. Okay. What temperature is measuring is the average kinetic energy of the molecules. The answer is that we will show you that stirring liquid warms it up. It's a matter of, the problem is you're going to lose heat faster than you gain it once you get above room temperature. It's hard. How do you keep the heat in? The key part of an oven is the fact that it closes. Okay. Okay, notice this says average. It doesn't say total kinetic energy. It doesn't say every molecule has the same kinetic energy. It says it's the average kinetic energy. Half are higher, half are lower. Okay? And they're changing all the time because every time they collide, they change speeds. One speeds up, the other one slows down, so it's constantly changing. So higher temperature, faster molecules. Higher temperature, faster molecules. Which means lower temperature, slower molecules. So you keep lowering the temperature, the molecules keep going slower. And you keep lowering the temperature, you keep going slower. How long can you keep lowering the temperature? No, not till infinity. I don't know. I can keep lowering the temperature until they stop moving. And you can't go slower than not moving. And that is absolute zero. That is absolute zero. Absolute zero is when all motion would stop. Now, I talked about it as molecule motion. It says molecular. Let's get rid of the word molecular there. When you get near absolute zero, the electron stops going around the nucleus. And the protons, neutrons, and electrons all just fall into this big lump where you can't identify one from the other. No, that's not plasma. It's the opposite. It's called a quantum superfluid or a Bose-Einstein condensate. Those are the fifth, sixth, and seventh form of matter. Okay. At low temperatures. 5, 6, and 7. There's a Bose-Einstein condensate and then two quantum superfluids. Okay. So what happens is you can't distinguish protons, neutrons, electrons from each other when you get cold enough, and then when you heat them back up, they separate back out. They don't know why.
I'm just saying, I'm not gonna try. But if you were to do that.
Well, first of all, you wouldn't get there because it's an asymptote. All you can get is closer and closer to it. You can't ever get the lowest temperature ever reached. And I could probably say the safe bet. Well, I could say in the known universe, it's been in Colorado. And it's within a millionth of a degree. Okay, but because space is warmer than that, and the problem is heat keeps leaking in. How do you keep the heat out? Okay, because if anything hits you, you're moving faster, and if you're not moving and anything hits you, you've raised the temperature. It's University of Colorado Boulder. They have a low temperature place. Okay, so this is what temperature looks like if you talk about the number of molecules, the percent of molecules. So this is a graph like the one when you got the PSAT back. They told you what percent got what score. Right? Does that make sense? So this is which percent has this much energy. And the different colors are different temperatures. Blue's a low temperature, red's a high temperature, black's a medium temperature. So notice what happens to the curve. First, at low temperature, I got a bunch right near the axis. And then as I raise the temperature, they spread out and lower down. I get fewer with that average, with that peak. Why? Because the area underneath the curve has to stay the same. Because what's underneath the curve is 100% of the molecules. So if you take and stretch that, if you want that curve to move, either it has to move as a unit, which means that you're leaving, not moving behind, if that's a possibility. Okay? Or you got to stretch the graph out. Does that make sense? Since you got to keep the same area underneath the curve, as I get the temperature higher and higher, it gets flatter and flatter. I get a wider range of kinetic energies. Okay? Now notice, very few molecules have high kinetic energy. But when I raise the temperature, more of them do. Those are the ones that are going to evaporate. Warm water evaporates faster than cold water because it's got more molecules that are moving fast. Right? I'll try to give evidence of those pieces along the way that you can see. That's why warm water, that's why you want to do your dishes in hot water, unless you like drying. Okay? And the average kinetic energy is the temperature, and you would think that it would be right down the peak of each one of those, but actually it's not. It's slightly past the peak because this one stops at the axis and the other one goes on forever. These lines technically go on forever, never quite touching the axis. Asymptotically, yes. so that the average is slightly past the peak. Okay. So temperature. The average kinetic energy is directly proportional to the temperature in Kelvin. Kelvin is a temperature scale named after a scientist who was the Lord of Kelvin. Lord Kelvin. Not Charles. It is Charles Thomson. Yeah, Thomson. Him. So if you double the temperature in Kelvin, you double the average kinetic energy. That's what directly proportional means. What happens to one happens to the other.
Comparison of Fahrenheit.
Well, we'll never do it. It's ugly. No, we'll never do it. It's wow. Subtract 32 and multiply by 273 465ths. Yeah, you don't ever want to do that. So if you change the temperature from 300 Kelvin to 600 Kelvin, the kinetic energy doubles because the temperature, the temperature's double. But we can only talk about doubling temperature if we use Kelvin. Okay? We can't do it in Celsius because Kelvin starts at 0. Notice my Kelvin temperatures don't have degree signs. I didn't forget them. It doesn't get them. Because a degree sign means somebody picked 0. That's why it looks like a 0. That's what a degree sign means, is somebody picked where 0 was. When you lay down a compass to measure an angle, you're picking where 0 is at. Right? That's why it's a degree sign. Okay? Kelvin, nobody picked 0. There really is a 0. They didn't pick some arbitrary number. Celsius picked 100 degrees, or picked the freezing point of water, right? So he gets 0 degrees Celsius because he picked 0 to be the freezing point of water, so he gets a degree sign. Fahrenheit picked the lowest temperature you could get an ice-salt water mixture to be 0. That's what he picked. You want to know what he picked? That's what he picked. Okay, the lowest temperature you get a salt ice water mixture. That's why it gets a 0. And hey, if you change the temperature from 300 degrees Celsius to 600 degrees Celsius, the kinetic energy doesn't double. Why not? That's twice as big, but I'll give you a better example of why it doesn't work in Celsius. Okay, so you go outside in northern Michigan and it's negative 20. It's cold, negative 20 degrees Celsius. And then the temperature doubles. What temperature is it? Can you see the problem? Because if you double it, it's negative 40. But if I double the temperature, it's getting warmer, not colder. The problem is Celsius has negatives. I mean, there's a relationship, but the math relationship is a little bit more complicated. It's a linear relationship, but you got to put b in there. Y equals mx plus b. You got to put that b factor in there. The fact that you don't start at 0. Well, the difference is 0 degrees Celsius is 273 Kelvin. So if you want to go between Kelvin and Celsius, here's the equation. Well, if you want to be really specific, you can put the 1.5 if you want to. We tend to leave it off. You usually don't need that many sig figs. So you can remember that you have to add 273 to figure out Kelvin. I don't remember whether I add or subtract. I remember that Kelvin's always bigger. As long as I know Kelvin's always bigger, I'll do the right math every time. Because I'll know if I got it wrong, because my answer will be less than when I started from. How important is this? Of the few things they put on here, one of them is Kelvin equals Celsius plus 273. It's on here. You have some homework questions on that tonight. I'm not going to work out any examples. I think you're okay with that. Okay, I didn't want to put you under too much pressure. But pressure is those collisions. Pressure is those collisions. And if you have completely empty space, how many collisions do you have? None. So how much pressure do you have? None. And that place we call, it should go the wrong way. We call that a vacuum. A vacuum is completely empty space. It has no pressure. Because there's nothing hitting. Pressure has several units. First one's atmospheres. And we said that STP was 1 atmosphere pressure. But pressure is the one that has the most units. It's because it's measured in so many different places, in different ways. In the US, we use pounds per square inch, PSI. That's what it says on your tires. How many pounds on each square inch of surface? Device they measure it with is called a barometer. And you hear the weatherman talk about it all the time, because he says, we've got a high pressure system. The barometric pressure is 30.07 and rising. What the heck is that 30.07? It's meaningless without units. I know the units. Okay, and the units are based on a device, the first device they used for measuring pressure. It's called a barometer. Okay, so let me show you how a barometer works. You start off with a long glass tube sealed at one end, and you fill it completely to the top with mercury. Then you put your finger over the thing, and you flip it over and stick that open end into the dish of mercury, and let your finger go. When you do that, the mercury will stay in the tube, just like the water stays in the straw when you put your finger on a Carl's Jr., for the same reason. Because up here is a vacuum, there's nothing hitting. Because it was full, and then it dropped down, I didn't leave anything behind. Here, the molecules are hitting, and the mercury wants to go someplace where it won't get hit. And it goes up there, because it won't get hit up there, and it can only lift it so far. It can lift it 760 millimeters high. That's 760 millimeters is right here. So it'll hold it up that high, column of mercury. So if the pressure's less, the column won't be as high, right? So a unit of pressure is the millimeter of mercury. Millimeter of mercury is a unit of pressure. In the English system, at 760 is right about 30 inches. The weatherman is talking about inches of mercury, not millimeters of mercury. He's just doing English system, not metric system. And 1 atmosphere, by definition, is 760 millimeters of mercury. That's what they defined 1 atmosphere as. The amount that will hold up a column 760 high. Okay. Now, the guy who invented this barometer, his name was Torricelli. So they named this unit after him and called it a Tor. Aren't you glad you don't have to call it, don't have to write out Torricelli? Tortellini, Torricelli. Okay. Okay. And the official metric unit is the Pascal. But the Pascal is a really tiny unit of pressure. That 1 atmosphere would be 101,325 of them. So instead of using pascals, we use kilopascals. Hey, and look, we got a whole bunch of things that are equal to each other. Guess what your homework is going to ask you to do tonight? Would you rather be teaching new stuff? I'm not going to do any of these. We're not going to waste our time in class. All I got to say is, you know how to do it, because you'll need it, because we got to have the right units to make the math work. Okay? So, and actually, you don't have to memorize them. They're the last thing on this list. One atmosphere is 760 millimeters of mercury, is 760 torr, is 101.325 kilopascals, 14.7 pounds per square inch, 29.92 inches of mercury. And the homework's there. I'm sorry I didn't work out any temperature or pressure problems for you, but I think you can handle them. There are examples in the book.